Good morning. I am Dr. Rajesh Kannan, Associate Professor, Head of the Department, St. Joseph's College of Engineering, Department of ECE. I am going to handle the topic is DFT, Discrete Fourier Transform. So before going to this topic, we are supposed to know what are the blocks inside the DSP. So let me start from the DSP introduction. So we have the DSP processor here. So the front part of the DSP processor, we have the A to D converter, and the output side we have D to A converter. So the DSP processor will take only the digital signal and it will process and it will give the digital output. So normal all signals are in nature, physical quantities are analog in nature. All the common existing signals are in analog in nature. So the first part, we need to convert the analog into digital. So we have to know what are the blocks inside this A to D converter. So inside this A to D converter, we have the first block is a sampler. We need to sample the continuous time signal, followed by quantizer. So we need to quantize the sampled version of the output, and finally we need to assign the binary bits to the analog value. That can be done by using encoder. So these are the blocks inside that A to D converter. So once we get the digital output, that will be given to the input of DSP processor. So finally the digital output can be converted back to the analog by using D to A converter. Okay. So let's start with this class. We are going to discuss the topic as DFT, Discrete Fourier Transform. So before going to this DFT, we must know what is the need of transform. So all the natural signals are in continuously changes with the time. It's all continuous time signal. Suppose if we want to analyze the power or energy, that could be that will not be possible when you are doing it in time domain. So we need to transfer the time domain signal into some other domains. It may be frequency domain by using a Fourier transform or Laplace transform, whatever the transfer depends on the application, we make use of those transforms. So now this class we are going to see discrete Fourier transform. So before going to this discrete, what is the evolution of this transform? DFT is, it starts from FT, Fourier transform. So whenever we want to analyze continuous time signal, we need to apply Fourier transform. But when you come for that signal processing, all signals are in discrete time nature. So when you want to analyze discrete time signal, we have to apply DTFT, discrete time Fourier transform. But what is the setback of the DTFT is there that omega is still it's a continuous variable. So we need to sample that omega. As a result, the final transform we derive as DFT, discrete Fourier transform. By using this DFT, we can able to analyze discrete time signal. So that can be, we will discuss the DFT procedure with the use of the application of 1 power. Let x of n is a discrete time signal. The DFT of x of n is x of k, which is equal to summation n0 to n minus 1 x of n e power minus j 2 pi k n by capital N, where the k ranges from 0 to n minus 1. This is the formula for the computation of n-point DFT. So with the use of this formula, we can able to transform the signal, time domain signal, discrete time domain signal into the frequency domain with the use of discrete Fourier transform. Once we complete the analysis in the frequency domain, again we convert back to the time domain with the use of inverse DFT. So that could be possible with the use of IDFT formula. So the IDFT of x of k, IDFT of x of k is equal to the final you get x of n, which is equal to 1 by n summation k equal to 0 to n minus 1 x of k e power j 2 pi kn by n, where n ranges from 0 to n minus 1. With the use of this, we can able to compute. This is a direct computation method for transfer the signal from time domain to frequency domain. This could be possible when the n is small and the n length is small. Smaller length of n, we can apply this direct computation methodology for computation of DFT. Suppose if n is large, for example, the n number of samples is 8 or number of samples is 16. When we apply this direct computation, that will be a very lengthy sequence and tedious one. So it takes a time consuming process. In order to eliminate these drawback excess in the DFT, we go to the next approach is FFT, fast Fourier transform. So fast Fourier transform is nothing but it is an algorithm or approach that can be used to compute the DFT with a reduced number of calculations. So we have two kind of algorithm approach under the FFT, fast Fourier transform. One is the DIT, decimation in time. The other one is the decimation in frequency. So the decimation in time is, from the name itself, we can define the DIT, decimation in time is the time domain is decimated. Time domain is decimated. And the another important point, there is a major differences between DIT and DIFS. First point, the DIT, the time domain is decimated. The second one, here the input is bit reverse order and output is a normal order. That is the second point related to DIT algorithm. And third, one of the basic equation, X is the computation of the DIT is A and B, whatever the output you get, that is after the complex multiplication, the complex addition will be carried out in DIT. These are the three important points related to DIT. Then we go for DIF, decimation in frequency. From the name itself, again we can define the first point here in DIF, decimation in frequency. The frequency domain is decimated instead of time domain. Here we are taking the frequency domain and that can be decimated. That's the first point. And second one, here the input is normal order and the output is bit reverse order. That is the second point related to the DIF. And the third, what is the basic operation exists in the DIF approaches? Here the output will be getting after the complex multiplication will be taken after the completion of complex addition. So that is the basic equation for DIF algorithm. Okay. So let's start the example, a problem from DIT, decimation in time. So let us consider the input sequence whose length is 8. For example, you take n is 8. So if the n is 8, your x of n will have totally 8 samples. So for example, I am taking the input sequences 2, 2, 2 and 1, 1, 1, 1. So totally we will have 8 samples. So now we are going to apply the FFT algorithm. When you go for the DFT approach, when you apply the direct computation method, you have the limit of summation limit is n is 0 to 7 and the k ranges from 0 to 7. So that is the time consuming. For avoiding that only we go for DIT first, decimation in time. So first step of the DIT is the input is bit reverse order. Whatever the sequence is given, that should be altered in the bit reverse manner. The bit reverse order is nothing but x of 0 and x of 4 and x of 2 and x of 6 and x of 1, x of 5 and x of 3 and x of 7. This order is known as bit reverse. So the given sequence can be arranged in this order. So our input of your DIT is whatever the sequence is given, that is in normal order. X of 1, 0, 1, 2 and 3, 4, 5, 6, 7. That can be rearranged into this order 0, 4, 2, 6, 1, 5, 3, 7. That order is known as a bit reverse. That can be the input of DIT algorithm. So our input sequence is 2. Then x of 4 is 1. Then 2 is 2. And 6 is 1. And 1 is 2. 5 is 1. And 3 is 2. And 7 is 1. So now this will take as an input of DIT algorithm. So now we start applying the algorithm process, and we start computing DFT, discrete Fourier transform. So the stage 1, and the flow of the computation is, the first stage we will be having 4 2-point, and second stage we will be having 2 4-point, and the final stage we have only 1 8-point. So let me start from the first stage computation with the sequences 2 1 2 1 2 1 2 1. So now before going to this, we must know what is the basic flow graph for DIT algorithm. As I said earlier, the input the output equation for DIT is capital A equal to small a plus b into W and T, and capital B A minus B W and T. That can be represented in flow graph. So let's start. Input is A and B, and the output is capital A and B. So you have the flow graph. Basic flow graph is this. So if you want to get A, you have the input is the adder. At the end of this point is we have the adder. So this A should reach at the end. So here you get A. That should be added with B into W and K. So B must be multiplied with the multiplication factor is W and K. That will be added with A. You will get the first output of your basic flow graph of DIT. And second, we need to get capital B, the second output. So the second output is, one of the input is A here. So that A you can take it from here. You will get one input to the adder. So you get A. And the second one minus B into W and K. So here you put the multiplication factor is minus 1. The final you get B into W and K. This is a way to get the basic flow graph for decimation in time algorithm. So with the use of this, our first stage computation is, we will be having 4 2-point. The sequence is 2 1 2 1 2 1 2 1. So we need to draw 4 2-point graph under the first stage computation. First stage computation. So we can draw 4 2-point graph, and the input is, first input is 2 1. The same way we can apply for the rest of the inputs. So all the inputs are, since all the inputs are same, 2 1 2 1 2 1 2 1, because the input can be splitted 2-point sequence. Total 8 can be splitted into 4 twos. So all inputs are 2 1 2 1 2 1 2 1, and here is 1 1, and the total factor value is W n by 4 power 0, that is W 2 power 0, that is 1, and here the multiplication factor is minus 1. So 1 1, and here 1 minus 1, and 1 1 1 and minus 1, and the final thing is 1 1 1 minus 1. For each graph we need to find output of each line. So the first output is here 2 plus 1, so you will get 3. And second output is, one of the input is 2. The other input is coming from this way. 1 into 1 into minus 1, we will get 1. Since all the inputs are same, we can get the same output 3 1 3 1 3 1 3 1. So that is the output of first stage computation. So after the first stage, we will be getting the output sequences 3 1 3 1 3 1 3 1. This will be the input to the second stage. So 3 1 3 1 3 1 3 1. As I said already, the input we have 2 4-point. So this can be split into 2 groups. One is a 3 1 3 1 is 1 4-point. The other 3 1 3 1 is second 4-point. So we need to do the calculation under the second stage by the use of 2 4-point DIT graph. So that is the second stage computation. Now the first stage is over. Now we go for second stage. The second stage, we can draw 1 4-point, 4 lines we can draw, and the first line to third line we can connect, we can form the butterflies, and the third line to first, the reverse process, fourth to second, and the input is 3 1 and 3 1, and here the multiplication factor is 1 1 1 1, and here is the total factor W n by 2 power 0, W n by 2 power 1. So W n by 2, n is 8 here. So W 4 power 0, and here is Wn by 2 is again W4 power 1. W4 power 0 is 1 and W4 power 1 is minus j. That value is minus j. Here is minus 1 and minus 1. We'll get. Now you can, as I said earlier, the same way what we have done it in first stage computation, we need to calculate the output of each node. So the first node you will get 3 plus 3, 6. And the second node 1 and here is minus j. And third node 3 minus 3, 0. And the last node, this node is 1 and here is plus j. That is the output of first 4 point. And here, since the second group is also the same sequence 3 1 3 1, we are getting the same output from second 4 point DFT graph. So the same kind of calculation. So no need to do it again. So you can join like this, and the input is 3 1 3 1. So if the input is different, your output also different. So here both the 4 point, the inputs are same. We can write the same output 0 1 plus j. From this we can get the output of second stage computation. So that output sequence what we are getting from the second stage is 6 1 minus j 0 1 plus j 6 1 minus j 0 1 plus j. This will be the output of second stage computation. Now we come for the last stage, third stage computation, that is a single 8 point. So whatever the output of the second, that will be a input of the third stage computation. So we need to draw one 8 point DIT flow graph with the input is the output of second stage. So that is the final stage of your DIT algorithm, that is the third stage. So you can draw one 8 point. So you can draw 8 lines, because since we have 8 inputs, all inputs must be given to this third stage computation. We need to draw 8 lines, and you can connect, you can form the butterfly 1 to 5 and 2 to 6, 3 to 7 and 4 to 8. The reverse process also 5 to 1, then 6 to 2, 7 to 3 and 8 to 4. The input is the output from the stage 1, stage 2, that is 6, 1 minus j, 0, 1 plus j, 6, 1 minus j, 0, 1 plus j. And we need to put the multiplication factor 1 1 1 1. And the lower side you have the 20 factors values are w 8 power 0, 8 power 1, 8 power 2, 8 power 3. W 8 power 0 is 1, W 8 power 1 is 0.707 minus j 0.707. W 8 power 2 is minus j, and W 8 power 3 is minus 0.707 minus j 0.707. And here you put minus 1. Because the twelfth factor formula is Wn is equal to nth root of unity, e power minus j 2 pi by n. And whatever the power is, 78 power 1 is 4 power 1, whatever it is. If n is 8, you can substitute 8, e power minus j 2 pi by 8, pi by 4, and cos pi by 4 minus a pi by 4, you can find the value. So using that formula, we can compute the value for all the 20 factors. Now, whatever we followed in stage 1 and stage 2, the same thing we can follow in stage 3. So you can compute the output of each node. So the first node again 12, and second you can 1 minus j1 plus the other one is from here 1 minus j into 0.707 minus j 0.707, and third one 0, and 4 1 plus j plus the other one is 1 plus j into minus 0.707 minus j 0.707, and the next one again 0, because 6 minus 6, and here 1 minus j, the other one is from here minus 1 into 1 minus j into 0.707 minus j 0.707. We need to simplify this. Final one real and imaginary, we can write it here, and the next one is 0, and the last one 1 plus j, and here plus minus 1 1 plus j minus 0.707 minus j 0.707. finally you will get the output, whatever the output from the third stage, that will be the normal order. That will be a final output of DIT algorithm. So finally we can get the x of k equal to the output from third stage. This is a way to simplify any kind of problem using DIT algorithm. So it's a time consuming, since the DFT is a time consuming, we go with DIT algorithm. Even n is 16 also, same way we can follow, because here whatever the algorithm or approach we followed here is radix 2 DIT algorithm. So whatever n value, that can be split into equally n by 2 and n by 2, and each n by 2 can be decimated into n by 4 and n by 4, two equal parts. This kind of decimation is continued until we get R point sequence. R is a radix. That is a here we are, whatever the discussion we are doing is a radix 2. So we are splitting the given sequence into two equal parts. One is the even sample, other one is a odd sample. So what if, for example, n is 8, that can be expressed as, since R is 2 power m, because the general expression is R power m. So R is a radix, m is the number of stages of computation. So 8 can be decimated into 2 equal 4, and 4 can be decimated into 2 equal to 2. So you will be having 3 stages of computation. So that could be possible with the use of radix 2 only. Suppose if we go for radix 3, whatever the sequence is given, that can be decimated into 3 equal parts. So that kind of procedure is totally different. So now this is the end of DIT FFT algorithm. Now we are going to discuss the basics of the next DIF, because the DIT is over. Because whatever the algorithm may be, your procedure may be different, the final answer will be same. Both the approaches used to compute the DFT with a reduced number of calculations from time domain to frequency domain, if your signal is a discrete signal. Now we go with the DIF, decimation in frequency. So as I said earlier, the major difference between DIT and DIF is, first point, here the input is normal order and output is bit reverse order. For example, we take the same sequence, x of n is equal to 2 2 2 2 again and 1 1 1 1. So the flow of DIF is also the reverse of DIT. So what we are seeing in DIT is the first stage is 4 2 point, followed by 2 4 point, and third stage is 1 8 point. Just you reverse, you will get DIF algorithm. So the first stage is 8 point, followed by 2 4 point, the end will 4 2 point. That is the way to proceed DIF algorithm. Same way, the basic program of DIF, like a DIT, the basic equation for DIF is for A and B both will be the output, and then A is A plus B and B is A minus B into W and K. After the arithmetic operation, we can multiply with the complex multiplication will be carried out. So now we are going to draw the flow graph for this basic equation. The same way you can draw the 2-point graph. The input is A and B and output is capital A and capital B. Now here the adder is at the middle. In DIT, the final end point we take it as adder. Addition will be carried out at that point. Here at the mid, the addition will be carried out. After the addition, the multiplication will be carried out. That is the major difference between DIT and DIF. Now, first, if you want to get A, you have to add A with B. So both will be added together. And here, finally you get A plus B. If you want to get B, capital B, one of the input is A. So A is from here. And another one is minus B. So multiplication factor is minus 1 here. After A minus B, here you will get A minus B. That will be multiplied with Prudent factor W and K. So you will get A minus B into W and K. That is the basic flow graph for DIF. So based on this flow graph, we can get the flow graph for all the 3 stages. As I said earlier, the first stage of computation in DIF is 8 point, but in DIT 2 point. So we have to draw 8 lines. 8 lines here. 8 lines. And you can connect the lines like this based on the basic graph. First to 5th and 6th, 7th and 8th, and the reverse process also. You can connect, you will make the butterflies here. The butterflies will be at the first stage in DIT. But in DIT, but even the number of butterflies are same. Total number of butterflies in each stage is n by 2 in both the DIT and DIF algorithm. That will not be changed. But the where we draw the butterflies, that will be different. But in DIT, the second stage will hold the butterfly diagram, and in DIF, the first stage will hold the butterfly diagram. That's it. So the input is a normal order. Whatever the sequence, that will be given here. Based on that, you can get the output here, and based on the basic graph, you can fix the multiplication factor. So first 4, 1, 1, and the rest is 1. Here is a minus 1 you will get, and this side is you get 20 factor value, W8 power 0, W8 power 1, W8 power 2 and W8 power 3. So you will be getting the output from stage 1. So whatever the output is stage 1, that will become an input to the stage 2. So stage 2 you have 2 4 point. Same way you can connect. The first stage you have a butterfly and another 4 point. The first output, 4 output from stage 1, that will be input to the first 4 point. The rest 4 will become an input to the second 4 point. From the 4 point you get some output. That will be an input to the stage 3. The stage 3 we have 4 2 point DIF graph. 4 2 point DIF. So the same way we can draw 4 2 point DIF graph, and each input you get it from the previous stage, second stage. So first 2 will become an input to the first 2 point, second and third and fourth. Whatever the final output you are getting from the third stage, that order is a bit reverse order. The first output is capital X of 0, second output is capital X of 4, and third one 2, 6 and 1, 5, 3, 7. This is the order which we received from the third stage of DIF. After that, we need to make the arrangement. We have to get the final DFT of the discrete time sequences X of 0 to X of 7. That is a way to solve the problem in DIF. The same sequence, 2 people will try. The same sequence you take and you apply the DIF. But whatever the graph may be, only the way, the procedure will be different. So in DIT 2 point, 4 point, 8 point. In DIF 8, 4, 2. Same way the butterflies will come the reverse order. So the second stage you get the butterfly in DIT, and DIF the first stage you will get the butterfly. So some of the slight changes will be there, but the final answer of both the approaches DIT and DIF both will be same. So once you completed your computation, you will be getting the final DFT answer. X of k equal to, you will get 8 sequence. For example, 1 plus j and 2 plus j, 4, whatever it is, 2 minus j, something you get. 8 sequence you will get. After doing it, we need to verify whether our answer is right or wrong. So in the final answer, your first sample is 8. This will be equal to sum of all the samples of your input sequence. Sum of all the samples. And the middle, for example, n is 8. Your middle sample is 4, x of 4. If n is 4, your middle sample is x of 2. The middle sample answer will be equal to sum of even sample minus sum of odd sample. And the remaining pairs, x of 1. Now we know the procedure for checking capital X of 0 and capital X of 4 for n is 8. And the remaining sample, it should satisfy one of the property of the DFT, x of k must be equal to x star of n minus k. The remaining pair should satisfy this property, conjugate property. So x of k means if the k is 1, x of 1 is equal to x star of 8 minus 1. That is x star of 7. So x of 1 and x of 7 both will be same, but it's a conjugate manner. So only the imaginary part, the sign will be reversed. So this is a way to check your final answer in DIT and DIF after the completion. Thank you.